Howdy, everyone. Someone please confirm that you can hear me. You probably have to unmute your mic.
Yeah.
We can.
Yes.
I hear you.
Okay, great. Thank you. Please stay muted until you have a question. Okay, so welcome to the spring semester and to Chemistry 322. I hope you're all doing well. I hope you're staying healthy.
Wait, what?
This is the largest chemistry class I've had at Texas A&M, and I've been teaching here for over 50 years. Most of you are isolated somewhere by yourself, so let's have a sense of this being a class. We had 183 people signed in, so please unmute, turn on your videos, and say hi to everybody.
Hi.
Hi.
Hello.
Hello.
Hi.
Howdy.
Hey.
Okay.
Hello.
Okay.
Hi.
Hello.
Okay, so please mute again. We have 173 of our 183 signed on, so I guess that's a fair percentage. I hope the other 10 find their way at some point. In any case, I'm Professor Jan Lane, and I'm going to be Zooming you through the physical chemistry course this semester. Things seemed to go okay last semester with Zoom. I think the students felt it went reasonably well. So these are strange times, but I think we can do okay. So let me move on and tell you a little bit about this course. And by the way, feel free to tell me if something's not working, if the sound's not right, or if you can't see the screen. I actually have my computer and desk facing a west window, so I have to be careful I don't get sun in my eyes, and if I glare out on you, please tell me, and so on. Okay, so this is physical chemistry for chemical engineers. This is what I call modern physical chemistry. A lot of stuff you learn in chemical engineering, like thermodynamics and distillations and things like that. That's what I call old-fashioned physical chemistry. So what we're going to talk about this semester has to do with atoms and molecules. So we're going to be down at the very small level of how things work. I've also written this course could also be known as ACA, energy levels and waves. So a lot of what we're going to talk about is what kind of energies can molecules, electrons, protons, photons, and things have. And the other thing we're going to see a lot of is that we have wave properties for just about everything. Everybody knows that light has waves, but we don't often think of electrons and protons and molecules as having wave properties. But a lot of this course is going to be related to that. Okay, so this is basically what we're going to talk about in this course. I made a list here. We're going to try to understand the universe at the atomic and molecular level. And most of this understanding is based on quantum mechanics. Quantum mechanics is going to tell us there are only specific energies and solutions that individual particles or molecules can have. And so that's going to be the basis of everything else. So questions to be addressed in this course include, what are the characteristics of an electron? I'm going to go out on a limb and say right now that you probably think you know what an electron looks like or what an electron is. By the end of the course, I think you're going to be more confused and really say, what in the heck is an electron? It's not just a little minus sign with a circle around it flying around a nucleus. It's going to be more complicated than that. Number two, in freshman chemistry, you learn to draw pictures of spherical s orbitals, kind of dumbbell-looking p orbitals, and then d orbitals, and maybe f orbitals. Probably you were not told why they look that way. We're going to see in this course from the mathematics of quantum mechanics why the orbitals look the way they are. Question 3, does light have particle properties? Well, I wouldn't ask that if the answer were no. In fact, the answer is yes, and we're going to call those particles photons. We've all seen science fiction movies, and you hear about photon torpedoes and everything like that. But indeed, light comes as particles, and they are photons. Number 4, do atomic particles have wave properties? And again, the answer is yes. As I said, the course is going to be a lot about waves. Number 5, what are chemical bonds? In freshman chemistry and probably continuing in organic chemistry, you would draw 2 dots between 2 elemental symbols. That would be a chemical bond, so-called Lewis dot structure. Or you might draw a single line representing 2 electrons, or a double bond with 2 lines representing 4 electrons. That's really a very simplistic picture of chemical bonds. We're going to look more carefully to see what they actually are. Number 6, where do colors come from? I'm going to contend that all the beautiful colors that we see in the universe are based on physical chemistry principles. So we will see where that comes from. It's going to have to do with electrons jumping between molecular orbitals and absorbing light, and that's where the color comes from. Lasers have now been around for over 60 years. We're going to see how they work. They're used all the time, of course. Anything from laser pointers to supermarket scanners to LASIK surgery and other medical surgery, as well as just spectroscopic experiments in laboratories. Number 8, this is something you might not have expected to hear in this course, but we're going to talk about where does the Big Bang theory for the creation of the universe come from. We're going to see the most fundamental aspect of this is based on understanding the hydrogen atom and how the spectra of the hydrogen atom tell us what the universe is actually doing and expanding and so on. I'll try to remember to tell you why the sky is blue. If I forget and somebody really wants to know, please remind me. Number 10, what causes global warming? Unfortunately, this is sometimes a political issue, but it shouldn't be. Just understanding the nature of the absorption of light by molecules can help us understand where global warming and the greenhouse effect comes from. Also, final 2 things. I'm going to contend that we would not have life on Earth if we did not have electronic transitions, those involved in electronic spectroscopy. So photosynthesis comes from that, and so we'll be talking about that to some extent. And then in the last third or so of the course, we're going to talk about statistical mechanics, and we'll see that an understanding of quantum mechanics as well as statistics will help us understand where the thermodynamics formulas come from, enthalpy, entropy, and things like that. Okay, so I sent everybody an attachment as an email, the syllabus for the course, so you should have that. In case you misplaced it or didn't get it, it's available on the Howdy website. And in fact, the one on Howdy is a little bit better than the one I'm showing you right now. The one I'm showing you, it was an older version, doesn't have the final exam date on it, and the PDF messed up a little bit. But in any case, we'll go over the version I have on the screen. So all of you know when we meet, I see we now have 179 people signed up. So I guess that includes me and probably the greater Joe. So we maybe have 6 people who haven't made it yet. In fact, Joe, are you there? Maybe not. Okay, I was going to introduce you. He has a very difficult last name, Joseph Puthenpouriel. he's going to be the grader for the course as such. So, oh, I'm sorry. The grader, that was my wrong course. The grader for the course are Dallas and Connor. Are you guys there?
Yep, I'm here.
Yeah.
Okay, so there was Connor, he's one of the graders. Is Dallas there too?
Yeah, I'm here.
Okay. You see both of the guys are on campus wearing masks, playing it safe. So hopefully everybody in the class is doing well. Okay, so you need to have a book for the course. The exams and material for the course, it's all included in the lecture notes, but most things I can only talk about once, and so it's very important that you go to the book and you read the appropriate chapters for it. That'll complement what we're talking about in class. Plus, there's a lot of problems in the textbooks that have been assigned and need to be turned in. So there are various ways to get the book. I was a little bit concerned when Barnes & Noble emailed me and said they were only ordering 47 new books, and we have 183 students, but they sell used versions. Many of you can get the books from Amazon and other places, so hopefully there haven't been major problems. Notice that I'm suggesting you only get volume 2 of the 11th edition. There's also a volume 1, or you can buy a joint version that has both volumes. Volume 1 is mostly on things like thermodynamics. So you've probably got most of that in your chemical engineering courses, and you don't necessarily need that. If you've had any problems, okay, I'm getting some chat messages, so let me see what those have to say. People say they can hear us. Okay, one fellow says that they have a PDF version of the book, whoever needs it. So you can read your chat and get the fellow's name if you want. Okay, lecture notes. I don't absolutely require you buy them, but I would say you're foolish not to. The cost, I think it was a little bit more than $25, but still not more than about $26. None of us make a profit on it. We just make it convenient for you to have all the notes. Plus, in the lecture notes, I've put many pages, I would guess 20, 30, 40 pages of practice problems in them. So that's a very useful thing to get from the lecture notes. I have another chat, see if that's about the lecture notes. Okay, it's again about the PDF version, about the book. Okay, so make sure you get the lecture notes. Some people are taking the course totally remotely, even overseas, and they've ordered the book, and I think pretty much everybody's going to be able to get it. If you do need to get it remotely and haven't, please call Barnes & Noble and try to arrange them to ship it for you. Okay, so you can read the syllabus about the course description. Pretty much of that is what I told you at the beginning about those questions that we're going to answer about why orbitals look like the way they do and why particles have waves and so on. Okay, we're basically going to have 5 topics that we spend quite a lot of time on, and then 2 topics that if we have time for, we'll talk about briefly. So the first 3 weeks or so, we're going to talk about basic quantum theory. So you're going to find this to be highly mathematical. I think whenever I teach this to chemical engineers, most of you don't have many problems with this. Right after this class, I have another PChem class, and that's for chemistry majors and biochemistry majors. And especially the biochemistry majors tend to have more problems with the math. But basically, we're just going to do basic differentiation. And if we have to do integrations, we'll do integrations from integral tables. If you look at the syllabus, that I sent you, or the one that's on Howdy, right at the very end, you'll see there's a math self-test. And that'll give you an example of what kind of mathematics you're expected to be able to do in the course. But as I said, I don't think you would have gotten to this point in chemical engineering if you were not able to do everything that's expected in this course. Okay, so when we talk about quantum theory, a lot of it is going to seem kind of esoteric and strange. It's not something that you can grab a hold of easily, but it's basically getting a feel for the mathematics. Once we've got the basics under control, then we're going to see how the quantum theory tells us why atoms look like the way they do, and why we get the spectroscopy that we get from atoms, the emission of light or absorption of light. Then we'll go on to talk about molecular structure. And then once we've done that and talked about molecular bonding, we'll talk about the spectroscopy that comes from molecules, things like infrared spectroscopy, electronic spectroscopy, and so on. And then the last major course topic will be statistical mechanics. Again, this is where the laws of thermodynamics come from, based on quantum mechanics and statistics. Hopefully we'll have a lecture or two time to talk about chemical kinetics and reaction dynamics, and be able to try to relate how quantum mechanics is related to this. Okay, I'll look at chat again. Okay, it's just discussion between students, so that's fine. All right, so we're going to have 3-hour exams, each roughly 18% of the course, and all the exam reviews are in class. So the PDF messed this up a little bit, all reviews during class, and here are the dates that we have for them. There will be a final exam, which will be worth the equivalent of 2-hour exams. This version of my syllabus was before the final dates had been assigned, but the final exam is on May 4th, I think 11 a.m., and it'll be on the syllabus that you should have, and the one that you have on Howdy. I have said the dates are tentative, just in case the course is running slowly or we have virus problems, whoever knows what else might happen. But in general, these are the dates that we will stick to. Okay, then you'll see there's a lot of problems assigned. I think there's something like 6 sets of problems assigned. The book is kind of goofy in its chapters. It has a chapter 7, then it has sections A, B, C, and D, and E, and F. And so the labeling of the problems goes according to which sections they are. If it has a capital E in front, that means it's an exercise, it's an easier kind of problem. If it's got a P, it's got a more difficult kind of problem. But problems have to be turned in on the due dates that you have. Dallas and Connor, the graders, are setting up eCampus so that the problems can be loaded there, or alternatively that they can be emailed to them. But as time approaches, we'll remind you about exactly how to do that. On a problem, if it says like 3A, that means you only do part A. There might be a part B and C. If it says 1, 3, or 4, even if they have several parts, do all of the parts. As I will tell you about the grading in just a second, the problems will not be individually graded for correctness. What we will do is we'll give you credit for effort. If you try to do all the problems, you'll get 3 points per problem set. So that might not seem a lot, but it'll add up to about 18 points in the semester, or it'll be about 3% of the course. So a lot of people, I shouldn't say a lot of people, but a few people each semester don't do the problems. They do lousy on the exams, and not having the problems even might lower their grade a notch. Okay, so make sure you do the problems. Here's the grading scheme. So Nominally, each hour exam is 100 points, but I always add an extra 10. So 110 points. And then I guarantee if you can get 90% on each hour exam, that'll be an A. I don't think I've ever had anyone get 100% on any of my hour exams, but don't let that faze you or bother you. The grades will be curved. And so it's to your advantage if you can sometimes even get over 100 points on an exam. Okay, as I said, problems, I said they were 15 points, but actually I think we have 6 problem sets, so they would be 18 points here. I also will almost certainly give you 3 unannounced pop quizzes. The purpose of these is to encourage you to attend class. I think instructors such as I have found that if we can get the students to regularly attend the classes, they will do much better. We'll see after the lecture if we can get it set up, but last semester we were able to do so. We're going to try to have all the lectures recorded and available on eCampus. So you can look at these again, but again, you're very much encouraged to attend the lecture as scheduled. If you don't do that, you might just blow it off and say, well, I don't really need to do that. Zoom also allows us to take class attendance very easily. It'll tell us how many people attended class. Right now, excluding the graders and me, we have 178 students. So five students at this point are missing, but hopefully they'll discover us at some point. Anyway, we'll grant 15 points for class attendance at the end of the semester based on the fraction of time that people attend. Okay, so again, problems, they're turned in. Credit will be given but not graded, and they're important since the examinations will include many problems. At the back of this syllabus is that math self-test, and it'll show you that we expect you to be able to do basic differentiation and integration using integral tables. Okay, I'm checking chat again. Okay, there's a question, do exams reflect homework problems or more in-class examples? We'll talk more about that when we review for the exams, but the problems I have stuck into your lecture notes are very closely related to what you can expect on examinations. The ones in the book, most of them are closely related to what you can expect on an exam, but some are just to give you a broader view of understanding what we're trying to teach you. Okay, please read up the makeup work policy and so on. Basically, the bottom line is, please don't ask to be excused from an exam or a pop quiz unless you have an authorized excuse for doing that. With as many students as we have in the class, it would be a real pain to try to write new exams for makeup exams. I cannot give the same exam at a different time that everybody takes together. So please do everything you can to take the exams exactly when scheduled. I think all of you, especially by now, you're mostly juniors and seniors. You know the Aggie code. An Aggie does not lie, cheat, or steal, or tolerate those who do. And I'm confident that all of you abide by that. There has been some discussion among faculty in other courses that with the Zooming methods, I guess especially if you have simple answers in geography or something else like that, people go to Google or other places to try to get answers. I fervently encourage you to remember the Aggie code. Anyone that wouldn't, years later, it's going to haunt you if you didn't. So please stick to that. All our exams are going to be open book, open note. So there should not be much requirement to try to get help from other sources. It'll be a matter of being able to figure out how to do the problems. Okay, so read the rest of the statements. There are safety statements, American for Disabilities statements. I've indicated we have attendance policy that we're going to record attendance, so you won't fail the course if you don't attend regularly, but you lose a lot of points, maybe making up 4 or 5% of the course, and that could hurt your grade if you don't. Someone asks, when will homework submissions be due? They'll be due the midnight of the day that they're indicated. And we do not generally post solutions for the problems. There's a solution manual that's available that you can have. It doesn't answer all of the questions, but if you have trouble with some questions, you can email me and I will try to answer that. Actually, in that regard, I should mention, I think at the top I indicated office hours. And so I have some time Tuesday and Thursday afternoons. My preference with as many students as we have in this class is that I try to answer most questions by emails. That way I can do them at times that are convenient. If I try to set up individual Zoom meetings for students, then there just wouldn't be time for individual questions like that. So try to get the answers by emails. If you have issues, I am happy to meet with you by Zoom. Okay, so let me stop the share a second, and I will share again. And one of the things that happens, can everybody see the where it says Professor Jan Lana?
Yes.
Okay. The last few years, it's started to become more popular among faculty to tell the students who we actually are. And I want to do that also because inevitably, if I don't tell you, people are going to ask me why I have such a strange name. In fact, constantly people don't know if I'm male or female. And one of the students in your class sent me an email before this class, said, howdy, ma'am, thinking that I was female. So I've oftentimes been confused being a Jean or a Joan or maybe the male version, Juan, and so on. Anyway, the name Jan is actually quite common in Estonia, which is not a very big country of 1 million people, which this would be the English equivalent of John. Now, so how did I wind up from Estonia to Texas A&M? Well, I had the misfortune of being born right in the middle of World War II. And hopefully, as all of you know, in World War II, we had 2 bad villains. Hitler, of course, was nasty in Germany, but Stalin was just as bad in Russia. And so in 1940, Hitler and Stalin divided up all of Europe, Hitler getting England and France and Poland and so on. And then the Soviet Union, primarily Russia, incorporated countries like Estonia, Latvia, and Lithuania, the so-called Baltic countries, which are south there of Finland and Scandinavia, into the Soviet Union. So you know about the Hitler aspects of it, so I won't say anything about that. But what the Soviet Union immediately started doing, they started to purge the populations of the countries they took over. They were very devout communists and they didn't want anyone opposing them. So the Russians basically came in and took over Estonia and annexed it to the Soviet Union. The US and Britain and other countries, by the way, never accepted that. So as far as Estonia was concerned, it was still a free country. Anyway, the Russians came in, and then Hitler decided that he wanted to invade Russia. And so the Germans came into Estonia also, and they drove out the Russians. And what that did is it left all the Russian documents behind. And my parents discovered that they were on the execution list. So my father was a deputy mayor of a small town in Estonia, and my mother was an English teacher. And so those were no-nos for the communists, because anybody with any kind of education was going to oppose communism. Anyway, so at that time, when the Germans came in, my parents, to some extent, felt that they may have been saved from execution by the Russians. Well, eventually, of course, then Germany started losing the war. The Russians came back, and they were about to come back into Estonia. And so my parents had no choice but to escape from the Russians. I had been born by that time. I think I was born under German occupation. And then our family of 5 basically had to just stay away from the war front. And we really didn't have a roof to sleep under for about a year. So eventually the war ended, and my family wound up in a United States sector displaced persons camp. And so we lived there for 5 years until finally my father, basically my parents, got permission to immigrate to the US. And so in 1949, our family wound up coming to the US, where first we went to South Carolina, where my father basically worked the cotton fields for a year. And then we moved on to Illinois, where he was able to get a job at a factory in a small town. The rest of my life was pretty much normal American. I grew up in a town called Polo, Illinois. I think you'll be amused by the name of the football team. It was called the Polo Marcos. I played football. I did pretty well. I got some distinction as a defensive back. I was more average as a running back. But anyway, it was pretty much normal high school. I then applied to the University of Illinois, got admitted. 2 weeks before I was to go to school, I got a letter which says, "Dear Miss Lana, since you have not obtained approved female housing at the University of Illinois, you cannot come." So I'm just giving you that as an example of the problems that I sometimes have to deal with my name. Anyway, they let me in. They gave me nice scholarships. I did well. And I went on to graduate school at MIT. Everything clicked very well for me. I graduated in 33 months. Most people take 5 or 6 years. They gave me a big award as the best graduate student. And even before I finished, down the road was Tufts University, which many of you probably heard of. It's the 3rd best university in the Boston area after Harvard and MIT. They have very good undergraduate education. They offered me a job without ever seeing me. And so I took it, since my wife was still in graduate school at the time at Harvard. My wife is now retired, by the way, but she taught at Texas A&M for about 30 years. She taught German also. Okay, so we now come to the point where I want you to appreciate things about Texas A&M. I don't know how many of you noticed when you come into the main entrance of the old chemistry building. And if you take the steps up and keep going forward, it'll say Arthur Martell Chemistry Hall. In my opinion, Arthur Martell did more to change Texas A&M than anybody else in its history. He was hired as the chemistry department head in 1967, and he immediately hired 15 new faculty for the chemistry department. Something like 10 or 12 were eminent professors at other universities. The university had given him license that Texas A&M should make a change. So in 1968, Texas A&M had 12,000 students, 6,000 were in the Corps, and all but 1,000 were male. Ladies were allowed to come to Texas A&M, but you had to have approved women's housing, just like supposedly the women at the University of Illinois did. But there was no approved women's housing. So the 1,000 women who were at A&M, they were either wives of students, wives or daughters of faculty members, but there was no approved housing. So it took quite a while until more ladies started coming. I think the Kruger-Dunn residence halls were built in 1972. Okay, so anyway, the reason I mention Arthur Martell is that he basically worked his tail off to try to get A&M to have excellent faculty who could not only teach, but who could also do research. And so he attracted me to come. I got some very nice research equipment, research support money, and he hired many other good people this way. And so this is what has turned Texas A&M to be one of the leading research universities now in the country. Okay, so just a brief summary here at Texas A&M. I've had about 40 PhD students get their degree with me. We published about 330 journal articles. I've been the editor of 4 books that are shown here, and you'll see these are topics we're going to discuss this semester, molecular spectroscopy among these. Also, for 25 years, I was editor for the Journal of Molecular Structure. That's another one of the topics that we cover in this course. Okay, let me look again, some chat questions. This must be before I explain it. Somebody asked me if my name was Dutch. Actually, I've seen my last name, Laane, in the Amsterdam phone book, so there must be a version of that. The Dutch spell my first name with one A, Jan, and they still pronounced it Jan. The people in Poland and Czech Republic and many other places also have the name Jan, but with one A. Okay, somebody's trying to collect $5 for doing the PDFs. Anyway, one student, Ron, has been to Tallinn. Good for him. I hope you liked it. The London Times rates Tallinn, Estonia as one of the 5 best tourist places in the world. It has many structures and buildings going back to about 1100 AD and stuff. Somebody else asked me why I quit being editor. It's pretty much the same reason why I'm probably going to be retiring in a year or two. At some point, you have to stop. So one other reason was I actually had very serious spinal surgery in 2018, and I had to be on sick leave for 2 semesters recovering from that. So that was a reason to quit. Okay, so I managed to waste most of the time, but I have time for a couple more things. I have to stop share again, share screen, and we will go back to here. We were on the syllabus, but now I can go to this. So, okay. little bit tongue-in-cheek. Now I'm going to introduce you to the whole world of science. And some of you may have seen this before, but nonetheless, I'll show it to you. So if it moves, it's biology, right? If it smells, it's chemistry. If it doesn't work, it's physics. If it doesn't add up, it's mathematics. And for you chemical engineers, we've added, if it leaks, it must be chemical engineering. And then the worst one, if it moves and smells, it's got to be biochemistry. So I'd like to show that to my biochemistry students. Okay, now I'm going to stop share again. And that's because I know chemical engineers do not take a course in inorganic chemistry. And I seem to have lost what I had. Let me try again. Hang in there, I'm looking for something. Okay, can everybody see the screen with the black screen?
Yes, YouTube.
Okay, so since you don't get a course in inorganic chemistry, I'm going to give you a cram course for doing this.
Now, here's a song I always get requests for, but I can't understand for the life of me why. It's simply the names of the chemical elements set to a Gilbert and Sullivan tune. I think the only reason I do it is to see if I still can. We'll try. There's antimony, arsenic, aluminum, selenium, and hydrogen, and oxygen, and nitrogen, and rhenium, and nickel, neodymium, neptunium, germanium, iron, americium, ruthenium, uranium, europium, zirconium, lutetium, vanadium, and lanthanum, and osmium, and astatine, and radium, and gold, actinium, and indium, and gallium, and iodine, and thorium, and thulium, and thallium. There's yttrium, ytterbium, actinium, rubidium, and boron, gadolinium, niobium, uranium, and strontium, and silicon, and silver, and samarium, and business bromine, lithium, beryllium, and barium. I left out one, actually. A new one was discovered since the song was written. It's called Lawrencium. So those of you who are taking notes can write it down in your programs. There's holmium and helium and hafnium and erbium and phosphorus and francium and fluorine and terbium, manganese and mercury and molybdenum, magnesium, dysprosium and scandium and cerium and cesium and lead, praseodymium and platinum, plutonium, palladium, promethium, potassium, polonium, titanium, magnesium, titanium, tellurium, and cadmium and calcium and chromium and curium. There's gold and californium and fermium, berkelium, and also metallium, einsteinium, nobelium, and argon, kryptonium, radium, and rhodium, and chloride, carbon, cobalt, copper, tungsten, and sodium. These are the only ones of which the news has come to Harvard. And there may be many others, but they haven't been discovered. Thank you. You may be interested to know that there is an older, much earlier version of that song, which is due to Aristotle, and which goes like this. There's earth and air and fire and water.
Okay, I hope you enjoyed that. I'm going to stop share again and then come back. Tom Lehrer, by the way, was a physics professor at Harvard, and he decided he could make more money in the 1960s being an entertainer. He has quite a famous record from that era. He has other songs called The New Math, another one called Pollution, and then he has other ones which I can't really tell you about because they would be inappropriate. But if you're interested, you can go and see what else he had to contribute. Okay, well, luckily for you, we can't get into much nitty-gritty of the course. Let me see what other chat comments are saying. Someone like Talim, they're jamming on the song. Someone points out Lehrer in German means teacher. That's correct. Someone asks, will we be posting lectures? So that's up to our graders. Dallas Freitas has promised that he will try to do that. He was successful last semester in posting the lectures. But if you tuned in late, I do encourage you to attend the lectures at the right time, and you get some credit for attending class at the appropriate time. Okay, so let me go ahead and use up another 2 or 3 minutes and just give you an idea of what our lectures are going to look like. I'm going to spend about 10 minutes, and I don't have time to do all that today, telling you about so-called classical mechanics. And this you would have learned about in physics, and this is what you normally live by. So for example, if you live in Houston, and let's say you're exactly 100 miles away, if you decide to drive at the nice slow pace of 50 miles an hour, you can calculate it's going to take you 2 hours to get there. So that's classical mechanics. If you want to drive 51.798 miles per hour, there's no problem. If driving were like quantum mechanics would say, well, it's okay to drive 52.3 miles an hour or 79.46 miles per hour, but you can't drive anything in between. So quantum mechanics is going to put a lot of constraints on things. But in classical mechanics, there are no constraints on energy or how fast something can go or where it is and things like that. When we get to quantum mechanics, we're going to talk about so-called quantized energy levels, or only the specific ones that work. But just to get started and point out some of the aspects of classical mechanics that apply both to large systems like automobiles and airplanes and so on, as well as to electrons, let's have a brief review of classical mechanics. So this will be Isaac Newton and others. All right, we're going to talk about kinetic energy quite a lot in the course. That's the energy of motion. We're going to use the symbol capital T. I don't know what your previous courses had. I think mine might have started with KE equals, but we're going to use the symbol T. So as you well know, kinetic energy is 1/2 the mass of what you're talking about times the velocity squared. So that applies to a bicycle, an automobile, to you running, and it also applies to an electron or a proton. Momentum, we're going to use the symbol P, and so that's going to be mass times velocity. And so you can see if we took momentum squared, that'd be m squared v squared. If we took p squared, momentum squared divided by 2m, that would be the kinetic energy. And you're going to see that I'm going to like to use this form when we get to talking about quantum mechanics. So we're going to have a kinetic energy term. It's going to have a second derivative instead of the p squared, but it'll have a 2m in the denominator. The other thing we learn about in classical mechanics is that you can have many kinds of potential energy. I'll just mention a couple of these. In physics, you no doubt learned about the potential energy of a spring. This is typically called a harmonic oscillator, and it's equal to 1/2 times a constant times the displacement from the equilibrium position. So 1/2 kx squared. We're going to talk about the harmonic oscillator quite a bit in the course also, because we're going to find the representation for a molecular bond can be a spring, and it works fairly well. And last example before I stop is just electrostatic contraction. We're going to utilize that this semester also. If you have two charges, the repulsion or attraction is given by minus the charge of the first particle times the charge of the second one divided by the distance between them. So if the charges are different, you'll get a positive potential energy. If the charges are the same, you'll get a negative potential energy. And we will be using this kind of potential energy when we talk about how nuclei attract electrons also. Okay, surprisingly, I don't see any more chat questions, but I'll pause for a minute or two to take any questions if you have. I do have a class coming up right after this one, so I won't hang on too long. Okay, well, I hope you all stay healthy. Hope you have a nice semester, and we'll get into real stuff then on Friday. Take care.
Thank you.
Thank you.
Thank you.
Thank you all.
Excuse me, Professor.
You too.
May I ask a question?
Sure.
So I've never had to purchase lecture notes before. Can you like describe to me, like you said that you don't require people to buy lecture notes, but like what is it that I would be purchasing?
It's basically everything that I'm showing you is in the lecture notes. Plus, as I said, there would be about 30 or 40 pages of practice problems that you have. So normally I had students purchase the notes even before we had the Zoom sessions, and people found it very useful that they could listen and concentrate on the lecture rather than having to try to jot everything down. So you have this all written out for you. So there's going to be a lot of mathematical equations and things, and you might have a hard time keeping up if you don't get them. I think it'd be foolish not to buy them, frankly.
Okay, great. Thank you very much.
Okay.